Welcome to Lecture 8 of Networks, Friends, Money and Bytes. Today's lecture will try to formulate and answer the question of how do I influence people on Facebook and Twitter. Now, network consists of both the topology, represented by the graph, and functionalities, which are the tasks carried out on top of the graph. In this chapter, we talk about topology-dependent influence model, in contrast to the population-dependent and topology-independent influence models in the last lecture. Now, as most of us know very well, that Facebook and Twitter have already become among the dominant communication modes, especially among younger people. Facebook started in late 2003, and by the time of spring 2012 of its IPO, it's got over 900 million users worldwide. And Twitter started much later, and by 2012 got over 500 million users worldwide. And one estimate says that within a day, it processed over 250 million tweets. Now, Twitter in particular provides what we call a directional link. Because you may subscribe to my tweets, but I don't subscribe to yours. And indeed, Twitter's success builds on top of microblogging, group texting, and one-sided or one-direction social networking. Now, given the popularity of these services, there's no shortage of interesting questions people have raised. One question is, how do I quantify the statistical properties of opinions on these platforms? For example, a recent study we carried out about tweets of Oscar-nominated movies. With about 12 million tweets over the month of February 2012, show that there is a very substantial positive skew of the tweets' opinion about these movies compared to other online platforms such as IMDb or Rotten Tomato. And statistical properties of the tweets alone did not provide insightful prediction of either the box office success or the critical acclaim. However, if it is combined with some of these other online opinion venues, then it does enhance the prediction accuracy. There's another question that is being addressed by a variety of companies. That is, how do I measure the influence power of individuals? For example, companies like Cloud computes what it calls the Cloud score. It combines your influential power on platforms such as Twitter, Facebook, and other kind of blogs into a numerical score. Now, how do they measure that? There are a variety of possibilities. For example, you can measure on Twitter the number of retweets of your tweets, okay, as we identify through RT of VIA. You can also look at the number of reposting of URLs that you posted. If you have access to the topology of who follows whom, for example, I follow your tweets, and you follow Alice's tweets, so on, then this topology can also give us some information about the influential power of different nodes, which are different Twitter users. Now, what kind of numerical scores is meaningful enough to be used? That often remains a question mark. And that relates to the third question: how do I leverage the above knowledge of the either aggregate statistical properties of Facebook and Twitter users' properties, or individual influential power scores, and turn these into viral marketing campaigns. For example, maybe I'll be able to seed some users and ask them to post or tweet certain information about my product or service. Now the question is, which nodes to seed? If I know the topology, will they help me to answer this question more precisely? So these three questions are indeed important, and as we will see, there is a significant gap between the theory and practice. Just like last lecture, this lecture offers the biggest gap between theory and practice in networking. And these questions are not entirely new either. The question of influential power of individual users got many interesting historical anecdotes. For example, the famous Revere-Dawes Ride that happened over the night of April 18th to 19th in 1775. This was the ride that helped alert the American forces to fight against the British military forces. Two individuals, Paul Revere and William Dawes, they both would like to alert the local American forces about imminent British action. They took different paths from Boston to Lexington, okay, and then they merged at Lexington and ride together to Concord. For example, this is the path that Revere took from Boston in Massachusetts to Lexington. And it turns out that the path took by Revere went through a lot more influential people in the neighborhood, and was much more effective in alerting the local militia leaders to prepare for the British military action, which led to the success of the first battle of the American Revolutionary War. So how can we quantify that a certain path pass through more influential nodes than other paths? Another very famous anecdote is this graph. This is a graph so-called the Paget-Florentian family graph, which shows 15 prominent families in Renaissance period of Florence, Italy. And 3 of these 15 families are shown here with their names. The Medici family was widely viewed as the most influential among the 15 families. If you look at this graph where each node is a family, and a link is a bidirectional link, representing some kind of kinship or marriage relationship, then how can we make intuitive understanding of this belief that the Medici family was by far the most influential? Well, if you look at a naive view, for example, how many links does each family have? Then the Medici family had 6 links. That's indeed the largest number. It's got the largest degree in this graph of family relations. But there are also other families, such as the Strozzi family and the Gaudani families. They also got each 4 neighbors. So the degree count is not that much of a difference. This is 50% higher than 4, but it was widely believed that the Medici family was a much more influential than a mere 50% differential. So how can we quantify this intuitive understanding of Medici's family being more important than just 50%? There's many other stories. For example, Granovetter, a famous social network theorist and empiricist, he did a 1973 survey in Amherst, Massachusetts, and discovered what he called the strength of weak ties. Turns out that if you look at the graph of people where each node is a person and the link is some kind of family of friendship relationship, then he showed that certain links which might be viewed as weak, for example, it goes all the way to another node, but there are very few other paths to connect this node to that other node, as opposed to these nodes which are very closely knit together. Later we will quantify the notion of a group in the advanced material part of the lecture. How do we quantify closely knit together idea? But intuitively and visually you can see that these nodes are very close together. Okay? And these links reach out to some far out nodes that are not tightly knit. And these are sometimes called weak links, and yet they present a high strength in disseminating information, such as employment opportunities. So how can we understand the importance and the utility of different links? In order to answer all these questions, historical ones, the current ones, we have to represent our important quantities with some symbols. So we start with, of course, graphs. This is already lecture 8. So in the past 7 lectures, we have seen quite a bit of graphs. You may still remember the graph of interference channel. You may remember the graph that represents the auction, the bipartite graph of matching. And now we're going to talk about graphs representing the topology of a network in general terms. And then we will use matrices to algebraically represent these graphs so that we can start running some mathematical operations. Well, in general, we say a graph, G, is a data structure that consists of 2 tuples. First is a set of nodes or vertices, it's the set V. And then is the set of links or edges, set E. Now each element in this set, say indexed by I, is simply one node. Okay? And then each element in this set is basically a 2-tuple, ij. It represents a link from node I to node j. If we say that ij is not equal to ji, then we call this graph a directed graph, okay? Because each link has a direction. Node I pointing to j doesn't mean that j points to I. Okay? Whereas if every link is actually both I to j and j to I, then we just skip writing these arrows on the line, and with the implicit understanding that this is a bidirectional link, and therefore it's a graph without directional links. In all the graphs that we'll be looking at, we look at the so-called simple and connected graphs. Simple meaning that each link just connects to 2 nodes, and connected means that every node is connected to every other node somehow, some way, maybe through a very long path, but nonetheless they're all connected. We don't have a disconnected node like this. Although in Homer problem we'll be looking at generalization into what's called the hypergraphs. Now we're going to use some matrices to describe these graphs connectivity patterns. We'll first look at what's called the adjacency matrix, represented as a boldface A. This is a matrix of dimension n by n, where n is the number of nodes. And this matrix is very easily defined. We say the ijth entry of this matrix is 1 if there is a link from node I to node J, and 0 otherwise. For example, if I have the following graph, okay, it's a very simple graph, nodes 1, 2, 3, 4, then the 4x4 matrix A has the following entries. Okay. 1 is connected to 3, so the first row would say 0 because there's no self loop, and then 1, 1, and then 0 because 1 is not connected to the 4. And then the second row would say it's connected to node 1 and 3, not 4. 3 is connected to 1, 2, and 4. And 4 is only connected to 3. Okay, so this is the matrix A for this graph. As you can see, the diagonal is all 0 because there's no self loops. A node does not point to itself. And it's a symmetric matrix, meaning Aij equals Aj, which is really an algebraic way to say that this is a graph with bidirectional links. Now, if it is a directed graph, the links have directions, then how do we define Aij then? It's defined the same way. However, the ij's may be 1, but ji's might be 0. For example, if we say 1 goes to 2, 2 goes to 3, 3 goes to 1, and 4 goes to 3. Okay. Then the new matrix would be the following. Okay. 1 goes to 2, okay, and 2 goes to 3, 3 goes to 1, and 4 goes to 3. Now, as you can see that Aij is not equal to Aji, for example. This is 1, but this entry is 0. A21 is not equal to A12. The second matrix that we actually use much less in this course is called incidence matrix. This is a matrix represented by A hat of dimension n by L. N, as before, is the number of nodes, whereas L is now the number of links here. So how do we define the entries of this matrix? We say A hat, ijth entry, equals 1 if node I is on link J and 0 otherwise. So it's a binary matrix where it's 1 if there is an incidence of node I on if there's incidence of link J on node I. For example, in the last slide we look at this example, 1, 2, 3, 4. Now the matrix A hat will look like the following. We first have to write down also the labels for these links. Okay, let's write down these links as A, B, C, and D. Okay. So these are the 1, 2, 3, 4. These are A, B, C, D. So happens that still 4 by 4 because number of links equals number of nodes in this particular example. So link A is incident on both nodes 1 and 2. Write down 1, 1 here, and 0, 0. And B is incident on both 2 and 3. C is incident on 1 and 3, and D is incident on 3 and 4. Now what if it is a directed graph? Okay, say the links are like this. Then we say the entry is -1 if node I stops, terminates J link, and it's 1 if node I starts link J, and 0 if node I is not related, it's not on link J. Okay. In this particular example, we see that node link A goes from 1 to 2, So start at 1, ends at node 2. And link B starts from 2, ends at 3. C from 3 to 1. It's actually from here, from 3 to 1, should be positive. And D is from 4 to 3. Okay, the starting point is positive 1, the ending point is negative 1, and 0 everywhere else. As you can see, every column of the incidence matrix of a directed graph must have exactly 1, 1, 1 minus 1, and the rest are 0, precisely because all the graphs we're looking at are simple graphs. But for each row, we could have multiple plus 1s and multiple minus 1s, because each node might start or terminate multiple links. So equipped with this basic set of notation of a graph and its matrices, now we can start to talk about how do we quantify the importance scores of a node.